Good morning, everyone, and very warm welcome on this Thursday morning. Thank you for joining us on the 5th Wekeo today on artificial intelligence applications using Copernicus data in Wekeo. It's our 5th webinar so far for those who are joining us for the first time. Today, we'll be introducing to you the platform and give you the first insight into the data and tools available useful for developing applications based on artificial intelligence using Copernicus data. Today, as usual, also we've lined up a number of brilliant experts for you who will give you and guide you on this journey and give you an insight on the journey and the use of the Wekeo TS. So this morning we have Mr. Svm with us, who has been involved in Wekeo user support as a senior advisor and has been in Copernicus user uptake activities as well for more than 50 years so far. Hello, good morning, and is an expert in Copernicus market development and user engagement. Next to Mr. Urovich, we have Mr. Neil Fletcher, who is the Digital Media and Outreach Manager at UMatsat. He has over 20 years of experience working as a science communicator for intergovernmental organizations. He is interested in data science and has background in marine science and conservation, fisheries, as well as remote sensing. Then we have Mrs. Julia Wageman. Good morning. And she is a geospatial data professional with a very strong background in Earth observation. She has designed and developed educational Jupyter notebooks of machine learning examples with Earth observation data as part of the online course Artificial Intelligence for Earth Monitoring of UMatsat. And finally, we have with us our expert, who normally always joins us as well for more technical questions, Mr. Amin El Amrani, who's a satellite imagery expert. He's a Wekeo user support expert as well, as I mentioned, specialized in technical issues. He deals daily with our user support issues as well. Yes. And without further ado, we're going to look at our agenda. Together with our experts, we'll give you an overview of everything you need to know about the Wekeo DS service. And so you have a thorough introduction as well to the platform and ready to dive in deeper with us in this webinar as well. Just to bear in mind, your questions will all be answered towards the end of the webinar. So do not hesitate to feel free to put your questions throughout the sessions in the Q&A as per usual. And today's agenda, without further ado, so we're going to have two parts as usual with a little break in the middle. We have Mr. Stefan Orovich opening with the speech and introduction for Wiki user support. Then we're going to dive into a presentation by Neil Fletcher, artificial intelligence applications using Copernicus data in Wekeo. And we will move on and give floor to Mrs. Wageman on Wekeo user support and with introduction, and then we'll follow the practical session as well, followed by Q&A, and that we should wrap up by 12:30 as usual, correct? So I've mentioned already the rules. You have the Q&A part, and without further ado, I would like to give the floor to Stefan Orovich. Right. Enjoy, everyone.
Good morning, everyone from Brussels. Let me share my screen, if I still know how to do that. Yes, I hope you can see it. So first, as usual, apologies to those who already heard the general introduction about Wekeo in one of our 12 or 13 previous webinars, but that's the subject we're going to be delving into today. Artificial intelligence applications is something that we've never touched upon before in those training webinars. Maybe there's some new faces, new people attending, so I will give you a general introduction about Wekeo. What is Wekeo? Wekeo is a one-stop shop access point to Copernicus data and information, which was put together by 4 of the leading organizations actually implementing the Copernicus services: EUMETSAT, the European Organization for the Exploitation of Meteorological Satellites, the European Center for Medium Range Weather Forecast, ECMWF, Mercator Océan International, and the European Environment Agency. What makes it special, there are quite a number of unique features of this DIAS being a data information and an access service. There are 5 DIASes, but Wekeo is unique, where there are still 5 DIASes for the moment, but things will change in the near future. One of the peculiarities is the fact that it's a distributed architecture. So the data doesn't get copied from its original repository into a new cloud, thus generating potential delays, potential latency, potential data not being up to date, and also generating like unnecessary consumption of electricity and obviously a negative contribution to the carbon footprint of Copernicus. So in that respect, through Wekeo, you have direct access to the data where it's regularly and normally stored, which is a great advantage. Not only does it guarantee that you have the most up-to-date data, but it also guarantees that because the 4 partners of Wekeo are either the producers or the custodians of a very large chunk of the Copernicus data, so the data from the satellites, the Sentinel satellites, and the data from the Copernicus services, you always have the most up-to-date version, A, and B, you have the products get ingested by definition in Wekeo before they get ingested anywhere else. So some advantage from that point of view. In Wekeo, you find 3 things, basically. The data, I'll come back to it, virtual tools and a virtual environment for processing and storage, and a user support. The user support is another one, and I'll come back to it also, is another one of the unique features of Wekeo, in the sense that here the organizations that have joined forces to create this DIAS, these organizations have the most expertise you can have on the data, because again, they either produce it or they contract its production to industry based on their own specifications. So who can best answer highly technical questions on the nature of the data, how to use it, give examples of use cases, but the 4 organizations that are the promoters and the shareholders, in some sense, of Wekeo. So data is not a copy, as I said, and you directly access the original sources. You have an expert user support that can really answer any question you would have, and has a very strict service level agreement by which it must answer your questions within a certain time frame. Otherwise, they get penalties, etc., because this is contractor operated. And a harmonized data access, which makes basically the experience of working with the data completely seamless because of that harmonized data access. And this availability of Jupyter notebooks, etc., and virtual workstations, cloud-based tools, etc. The platform was designed to serve basically all types of users, from civil society, and I say this because you have a viewer that enables you to discover the data, look at the data, download the data, that doesn't require to have a PhD or even a master's or any particular experience in Earth observation. Institutions, private sector, quite a lot of applications, operational applications are running on Wekeo and are being delivered either to the Copernicus services or just by businesses that have clients, customers to which they deliver a service, and also quite a large user base with scientists in academia or in research centers. The data catalog. So in Wekeo, you find the largest offer of Copernicus data, largest because by definition, to take the example of land monitoring service, for instance, well, the European Environment Agency, which is responsible for implementing the CLMS service, well, every new product is going to be on Wekeo. So the 4 partners put at your disposal the data from Sentinel-1, so radar, synthetic aperture radar data, so obviously dealing with being able to acquire information even over clouds and at night, Sentinel-2 high definition optical, Sentinel-3 medium definition optical, and sea level, sea surface temperature, and other similar attributes, and access to the largest possible set of information from the Copernicus Atmosphere Monitoring Service, Marine Environment Monitoring Service, Land Monitoring Service, and the Climate Change Service. And as said earlier, an infrastructure to store the data, tools to process the data and store it, a quite sophisticated user support and user development and management. You have a very large database of wikis, of training documents, of frequently asked questions, etc., and a marketplace which you can use freely at no cost to basically showcase the things that you've developed, the applications you've developed, the algorithms you have developed using Wekeo as a storage and processing platform, access, storage, processing and storage platform. There are currently, the latest count, 310 data sets stored in Wekeo, but every time there's a new product or a new data stream, for example, the Sentinel-6 Michael Freilich data, our satellite that basically measures sea level, the sea level to monitor sea level rise, that data will soon be available in Wekeo. So you'll have the number growing. We have quite easy to use viewers that enable you to browse through the data and to basically select the data that you want to download. Our user support, there's a level 1, which answers really quickly simple questions, but it's fully supported by senior experts from EUMETSAT, from ICMWF, from Mercator, and from the contractor team of the Wekeo user support. And as said earlier, quite a lot of support material. A lot of documentations, catalogs, Jupyter notebooks, drives, virtual machines. It's really, really the most complete offer in terms of both the ability to receive support and the availability of already published training material and support material. All the webinars and training sessions that we have organized since the beginning of the Wekeo DIAS is available on our YouTube channel, and I believe that even that number's 42 videos is outdated in the sense that I think the last webinar put the number to 43. This is the 5th of a series of 6 webinars of the first half of the year. We've had a few generic webinars, but today, again, we're going to specialize on artificial intelligence applications. We're on Facebook and Twitter. We try to announce all our events and to present some use cases, etc. So follow us there. There's a dedicated page to request support. You can either fill in the form, or you can send a an email to support@Wekeo. We also take questions from social media and answer them as if they were asked through the platform. Pricing. Many things are free in Wekeo. In particular, to browse the data, to download the data, to visualize the data, etc., is completely free. It's only when it comes, or even to promote your work is free. The only thing that is you have to pay for is computing power and storage, because that obviously has a cost, and the users are required to participate in sharing that cost with the European Commission, which is the funding source for Copernicus, obviously, and for Wekeo. So you can discover the data, download the Jupyter Notebook area. The Jupyter Lab is for free. And again, the only thing you have to pay is the advanced users. And there you see the prices range from 125 euros a month for the basic access to higher numbers for really companies that are running operational activities. I just would like to underline the fact that we have rather generous trial periods, 5 months for the D-Lite version. And if your application is really interesting in terms of either its novelty or its socioeconomic impact, like you're really tackling a major problem, there is quite some flexibility in providing researchers with extensions of these trial periods, because we're obviously eager to acquire and help develop new use cases to show what can be done with Copernicus in general and with Wekeo in particular. Our Jupyter Lab is a very interesting resource in which you will find quite a number of Jupyter notebooks with the full documentation, which will help you to train with the use of Wekeo and Copernicus data, or Earth observation data, for those of you who are not experts. So join our community, look back into our repository of previous webinars, and I do hope that you will enjoy today's webinar, where our experts will give you the keys on how to use Copernicus and Wekeo for AI, machine learning, etc. applications. So I now gladly pass the mic and the floor to Neil Fletcher for his presentation. Thank you for your attention, and I'll be glad to participate in the Q&A session towards the end of this webinar.
Okay, thanks, Stefan. I'll just share my screen. Okay, good morning, everyone, and thanks for joining this webinar today. So, yeah, I'm Neil, and I work for EUMETSAT. And so what I'm going to be talking to today about briefly is about the AI for Earth Monitoring massive open online course that we organized. And we organized this last year. And the idea behind the course really was that we know there's a huge amount of potential to work with machine learning data and Earth observation data that's available from the Copernicus program, whether it's managing large data sets or finding new insights with data, or even generating new products and services. And so what we wanted to do is to try and pull together some really good examples where people are kind of leading in the field of developing machine learning applications with Copernicus Earth observation data and services. So the idea was to try and kind of pull all this information and then open it up to people to come and learn about what you can actually do with some of the Earth observation data using machine learning techniques. So yeah, so the idea was to kind of bring people together to kind of understand how to access data, and also to access data via the Wekeo platform. So to kind of give good examples where people are able to follow how to access data, and really kind of help people start on a journey using machine learning and Copernicus data. So the idea behind the MOOC is it can be followed over 6 weeks, and we wanted to cover as many of the topics that are relevant for people related to Copernicus data within the MOOC. So the first week is all about a kind of introduction to Copernicus, and then we've got information about AI and machine learning techniques. And then we've got a week looking at land monitoring, and then oceans and atmosphere and climate. And then within each of those weeks, we provided examples, which I'll come on to in the next couple of slides. And the good thing about the course really is we have over 40 individual contributors, and there's more than 50 videos within the course. And one problem we had obviously was the last couple of years with COVID. Normally we would have been able to film people and go around and film lots of people to make a massive open online course. But for this, because of COVID, we had to get people to kind of self-film, which in one way worked because it meant that we were able to actually film a lot more people. So that's why we've ended up with more than 40 people involved in the course. So if you joined the MOOC, you'll find this is a kind of overview of week 3 and week 4, just to give you an example. And if you haven't followed MOOCs before, the idea is that you have lots of video content, and then you have static text content, and then you also, we wanted to provide more of a hands-on side to the course. So if you look, so here on the land monitoring topic in week 3, we've got information about different ways that you can monitor land using Copernicus data. And then further down, we start to introduce Jupyter Notebook tasks, where we're basically providing examples, example Jupyter Notebooks, where people can use machine learning techniques and actually follow through the code to see how to actually run it and how to work with the data. And with each notebook, I sometimes find working with the Jupyter Notebooks, I have a lot of code and I don't always understand all the bits when things go wrong or there's issues. So for the notebooks, we organized with Julia, who'll be speaking later, to develop some YouTube tutorial videos where she actually talks through all the bits of the code to really help you understand what everything is doing and what all the bits are doing and how it all works and how it comes together. So this is an example of the land week, and then we've got the oceans week, and there's lots of really interesting topics in there. There's a notebook task looking at tracking ships, and so you can actually click on that and look at a Jupyter Notebook and actually learn how you can use machine learning techniques to work with Copernicus data. So the way it works is if you want to join the MOOC, you go to FutureLearn, where the course is hosted, and then you can register, and I'll show you that in the next slide. And then you also can join Wekeo, and then you can access all the code and all the Jupyter Notebooks, or you can access the notebooks via the GitHub site, which I'll show you as well. So yeah, it's a mixture of video and interactive content, and the notebooks, we've got 18 notebooks on the course, so there's a good range of topics there to hopefully give you some new ideas and see how you can use machine learning with Earth observation data and maybe come up with new and innovative ideas. So here's the overview screen on the FutureLearn platform, and so we can see we've just nearly got 10,000 people have enrolled on the course, so that's really good. There's obviously a lot of interest in joining it, and the way you can join is you can, if you want to pay and get a certificate to do the course, FutureLearn have an offer here which you can do. If you just want to join the course and look at all the video resources and look at the notebooks and see all the comments from people, then you can just join here where I've put the red box. So you can join for free, and then you have access to everything for 6 weeks to look at all the content. And what we're doing is the course will be available on on Future Learn until October, and we want to then put all the content onto another platform so that people can continue to access it. And we've also put all the notebooks on the Wekeo GitHub site. So all the notebooks are here, and within the notebooks, you've actually got the YouTube videos as well. So you can actually follow each of the notebooks and really understand how everything works. And I mean, I think the thing about the MOOC is it can be used as a bit of a reference if you're wanting to really learn more about machine learning techniques and how they're being used. And there's various other initiatives that are going on around the EU where people are really trying to start working with Copernicus data and machine learning techniques. So there's it hopefully will be useful for you. And if you have any comments or ways we can improve, it would also be really good to hear from you, because all feedback is good to get so we can try to improve it. So yeah, so that's really about the MOOC. And now I think I hand back to Stefan, and I'll finish there.
Yes, well, I have nothing to add other than I want to stress the incredible success of that MOOC. You didn't mention that, Neil, but I saw from the screen 10,000, very close to 21 or 23 people away from 10,000 participants with a 4.5 star rating. And that's an average over 10,000. So this shows by itself the quality and the interest that this MOOC has generated. And I think it was a great initiative by UMITSAT and the Wekeo partners to develop it, because and especially as you will be migrating it so that it remains available to the community. I think it's a great resource, and it's really interesting because there are. Well, it's pretty obvious that AI can be used to plow through the data, to extract features in a semi-automatic way, but also to plow through the big data, which becomes very difficult to process fully manually or with human intervention. But also, when you think of it, the techniques that are used to extract features from medical imagery to identify diseases or issues, medical issues, are very close to those that you could use to extract features from Earth observation. So what this MOOC hopefully has allowed, and hopefully this webinar too, is to bring the AI community to EO, as much as showing the EO community how much the AI can help it and its users solve challenges and issues. So I think that MOOC is really a very valuable resource. Before we go into the demo, there's one question which we can answer now from Cesar Augusto Uthman, who is asking whether we can find data related to natural disasters or emergency. There, I can already make one point. There's two different ways of answering this question. To the question, is the data from the Copernicus Emergency Management Service available in Wekeo? The answer is no. But as you can import into your Jupyter Notebook data from basically anywhere, you can easily download the emergency management data, management service data. In most cases, is just vector data, so it's a zip which can easily be downloaded and then uploaded into Wekeo to combine it with other information such as land use or whatever. So the maps produced after disasters are not directly available, but it's a super easy technical process to include them. If the question is, can you work on disaster risk reduction or disaster management with using Wekeo? The answer is obviously yes. Yes, you can use the Sentinel 2, Sentinel 1, mainly because of the high resolution and the high revisit time of the satellites. You can definitely perform such applications in Wekeo, and there are use cases of people, in particular for forest fire monitoring or flood monitoring, using Sentinel-1 particular capabilities to distinguish bare soil from wet soil. So this can definitely be done in Wekeo. But without further ado, I think we can directly switch to the more technical presentation, which I'm sure is really what most of the attendance came here for. So I pass on the floor to Julia for her presentation.
Thank you, Stefan, and thank you also, Neil, and also a warm welcome and hello from my side. Great that you all joined the webinar today. Because we will have a 10 minutes break, so for the next 10 to 15 minutes, I will just give you a short introduction on how you can, in fact, access the Jupyter notebooks, what Neil already introduced you to. I already in the chat, I shared with you the GitHub repository where you can also get access to the notebooks and also the data. So this is also important, and you can clone the notebooks onto your local directories and local machines. And you also have instructions how you can do this. But before we start, I would like to actually ask you a couple of questions. And I just start also sharing my screen. And I ask you to go to slido.com and enter the hashtag AI4EM. And I also post in the chat a direct link to the Slido. And I just have a couple of questions because we saw that there's a lot of people enrolled in the course, and we basically in our first question interested. So why you are interested in artificial intelligence for Earth monitoring? So you might basically need it for your studies, or because it's a hot topic and you're interested in the topic, and specifically also the applications with Earth observation data. So this would be great to learn a bit more why you interested in the topic and why you're also joining today. So I see people are on the platform, so 16 participants are typing. Okay, so we see it's a part of your PhD work. It is a hot topic, exactly. It is for your, so specifically for small scale fisheries applications, because it's interesting, yes. But I see there's a lot for research and for PhD studies, flood forecasting, solar power forecasting, okay, coastal zone monitoring. Okay, this is super interesting. Thank you for sharing. Climate change monitoring, satellite altimetry. Okay, this is very interesting. Thank you. Thank you. So this is super also helpful also for future courses such as the MOOC what we developed last year. So basically, I then stopped this poll and I open the next question, which is how would you rate your level of expertise in artificial intelligence and machine learning for Earth monitoring? Okay, we have some experts, but certainly we are on the beginner level. Some also would rate their level on medium level. Yes. So yeah, I think this is that's also good that because it is a hot topic, but it is also a very new topic. So, and for this reason, the massive open online course last year was also developed to get a nice overview of different application examples. So that's good, basically. And so if you're a beginner, or I would also say if you're medium level user and researcher on AI and machine learning, the MOOC is certainly something and will give you some ideas. And I also would say if you're an expert, There's so many different application examples, so there's even also a chance that you can go there and also learn something new from the variety of different application examples the MOOC offers. And then we have just one final question. Are you one of the almost 10,000 people who subscribed to the MOOC on artificial intelligence for Earth monitoring last year in November? Okay, so we already see that some of you already joined the course, and we also hope that you enjoyed it and you were able to follow it. But still, the 60% of today's participants didn't have a chance to join. So there is, as Neil indicated, there is still the chance that to join. And today we will also show you how you can access specifically also the practical part of the MOOC with the help of Wekeo. And okay, good. So thank you so much. And then basically I will just give you now, okay, I just put this on here. So as I said, there are like different ways how you can access specifically the practical notebooks, what we prepared for the massive open online course last year. As Neil already indicated, and I shared the link already in the chat, this is the GitHub repository where you get all the content of the MOOC, including the data from. And also additionally, you also get an example on how you can install and clone the content and set up the environment you need to run and execute the notebooks on your local machine. So this is one way if you're interested to run the notebooks locally. But another and I would say also more convenient way, because there you don't have to set up your own environment. You can directly go to wekeo.eu, and Stefan gave already a very nice introduction on all the functionalities Wekeo has on offer. And I will show you now how you can, in fact, access notebooks and the Jupyter Hub environment that is on top of the Wekeo cloud repository, which helps you then also to access the data from Wekeo, but also to already develop workflows and processing steps with the data. And so in case you don't have an account yet, you can go to register and you can create an account. In case you have an account, then you can go on the top right to sign in, and then you're asked to sign in to Wekeo with your username and password. And I also do the same. I just need to copy paste also my credentials. And basically, I access it with my username and password. And once you're then signed in, you will see then basically on the top, instead of signing in and register, you will see on the top right, you will see dashboard and sign out. And then you can go to dashboard. And the dashboard gives you information about your user profile. But important here is on the left side navigation menu, there is a tab with Jupyter Hub. And if you click on there, then you will be redirected to the Jupyter Lab interface. And there will be most likely, so this is because I already logged in this morning, but if you log in, there will be basically an interface coming showing which different kernels you want to use. There will be like a regular kernel which is based on Python 3, or there will be also an option for machine learning. And this is important that specifically for the machine learning notebooks that you choose the machine learning kernel, because this has more processing power for you to also execute the notebooks and the machine learning examples. And so once you then chose the machine learning kernel, you will get an interface that shows you that your interface will start. And once it is started, you will come into an interface that looks like this. And I expect, so we had also some already who joined the MOOC last year, but I also expect that quite a few are already familiar with the interface of a Jupyter Lab environment. But just for those who haven't seen this interface yet, so basically it looks like kind of a file system you're probably familiar with from your workstation, Windows or also Mac. So you have on the left side a folder structure where you can access files. And here this indicates also that you're in your working directory. And then here you have the launcher interface, which gives you different options to open different functionalities. So you can open a notebook, a Jupyter notebook with different kernels. And a kernel means that basically there are different configurations for a specific kernel. So what I already said, for the machine learning kernel, we have just more powerful configurations, because for machine learning applications, we need more processing power. But we can also, if you more comfortable to work on the console, you can also just start a console and working with Python. And also you can manage your environment and your setup and open up a terminal interface and install additional libraries in case you need some. Just also to let you know that the machine learning kernel here already has all the libraries you require to execute the machine learning examples and to execute the notebooks. So this is just a general overview. And then on the left, you will see two folders. And the folder that is important to you is the public folder. And in this public folder, you see a list of other folders. And so in case you're interested also in other applications related to Wekeo and specific application domains like atmosphere, climate, or land, and these notebooks are more like introducing you to the different application data that is available on Wekeo, then you can have a look also to these notebooks in these folders. But for today, for the machine learning and AI examples, you have to go to the folder ML, which is for machine learning. And then if you enter into this folder, you will see the same structure what you also see on the GitHub. So we have different folders following the different weeks of the MOOC last year. So Neil already introduced you to that. We had like more like an introduction week that introduces you more to the topic artificial intelligence and machine learning. And then we have like the last 4 weeks, we had like application specific examples on land, ocean, atmosphere, and climate. So if we go into one folder, so for example, the one on land, then you see here the different examples we developed for the specific application area on land. And so for land, we have like an example on a tile-based classification with Regressor data, so which is a classification data set or training data set you will be introduced to, or a soil moisture estimation, or an example on a land cover classification with Sentinel-2 data. So if we go also then into one folder of one specific example, you will see that each example brings you everything you will need to execute a notebook. So we have the 2 notebooks here, which showcases examples on a supervised classification and examples on unsupervised classifications. But at the same time, you also have already the Sentinel-2 data available that is required, and also the training data and validation data that is required. And if we then open one notebook here, for example, so this is basically the common setup of, so yeah, just to open a notebook, it's simple. You just double click on it, and then in the main window, the notebook opens. And here, each notebook also has these introductory and overview videos what Neil introduced you to. So if we execute this, then you basically will be able to directly also play the video in the notebook. So in case you learn better just by listening, then this is also an opportunity for you to listen while I walk you through the notebook and the workflow and the example. And at the same time, you can also follow the notebook and the different steps directly here in the notebook. So there's like different ways of learning, which we also try to integrate into the notebooks. And then each notebook gives you an introduction to the example and the machine learning problem, and also the machine learning model that is used, and also the data, and at the same time also further resources, so that you also get additional information on the machine learning algorithm that has been used, or sometimes if it's a very scientific application or example, then we also link you to some scientific articles that give you an overview to the problem, etc. So after the break, I will then go through for each of the weeks of the application weeks, I will go through one example on one machine learning example, and I guide you through to get that you get a better overview on what application examples we included into the MOOC last year. But before we do the break, I also just want you to introduce you generally to the topic on artificial intelligence and machine learning, specifically for Earth observation and with Python. And so if we go back again to our machine learning folder and to the main overview of the MOOC Jupyter Notebook content, you can go to the first folder, which starts with 2. And this gives you more like an introduction to machine learning and artificial intelligence. And if you go to the folder 2C, Understanding Machine Learning Workflows, then this is just a more theoretical introduction on what it actually means to develop a machine learning workflow, and also the different steps of how you develop a machine learning workflow, what are the different steps, and also the principles of machine learning. So what are the nomenclature and also phrases and names used for the different steps, because machine learning is a hot topic, but this is also like specifically if you're beginner, it's also good to understand what is meant, for example, with inference. So to understand the nomenclature of why do you need training data, why do you need validation data, etc. And so this notebook introduces you to the essential steps, which are in particular, first of all, before you dive into a machine learning example and algorithm, the most essential step is to understand your machine learning problem. And this is what we tried to make clear here, is that basically, because it is a hot topic, you often also see that for any challenges or problems, people just apply machine learning, even though sometimes it might not be needed. So it could be also that sometimes just much simpler approach could be also the best approach, or a better approach. So this is important to understand your problem at the beginning. And also then we gave here an overview on what is actually meant by artificial intelligence, which is more the science that studies the way how to build intelligent programs and machines that can solve problems. And then machine learning is in fact a subcategory of artificial intelligence in general. And this provides a system provides the ability to learn and improve based on experience. And then deep learning, again, is a subset of machine learning, which has specifically neural networks as a backbone. And I think this is also important to understand when you start with the topic. And then we guide you through different machine learning categories. So that, like, there is supervised learning, and also we give you an overview of different algorithms that can be used for this specific machine learning category. Like a classic application is classifications in general. And their popular algorithms are decision trees or random forest. You might have already heard support vector machine or logistic regression. And then basically we also link here for each category also examples. So in case you're interested in this category, we also link you to the examples of notebooks that basically deal with this specific machine learning category. So we have supervised learning and unsupervised learning, and we give here also a common unsupervised learning algorithms, and again an example on unsupervised classification algorithms and of a notebook where we showcase you different algorithms. And also reinforcement learning. There's also an example at week 2, right at the beginning, to learn more about how reinforcement learning can be applied with Earth observation data. And then the second category is the deep learning or neural networks. And you see already that deep learning and neural networks is also a very popular category that is applied specifically with Earth observation data, and because we have quite a few examples that are part of the MOOC that apply, in fact, neural networks and deep learning algorithms to the problems. And yeah, so there's like convolutional neural networks, recurrent neural networks, or self-organizing maps are part of the deep learning or neural networks category. And then basically I just invite you to go through the examples, because we just also give here a list on what are common pre-processing steps specifically for Earth observation data that are needed to actually execute AI and machine learning examples. And here you see already that, like, in fact, the data preparation part is often the most time-consuming part, because building and training the model is specifically with the Python libraries that are already available at the moment and nowadays. This is actually compared to the data preparation part, just like a small amount of time. But preparing the data, for example, to get labeled data in order to classify some data, or to georeference and subset data, or to resample it, this is usually the most time-consuming part. So this gives you an introduction to the machine learning workflow. And then, in case you really haven't done any machine learning examples with Python, there is another notebook that also gives you a short overview on Python libraries for machine learning. And also that gives you a better overview on what is actually the difference between these different libraries. And so we provide you here an overview on, you might have already heard them. So we provide you a short introduction to TensorFlow, to Keras, to PyTorch, and scikit-learn. And these are also all the libraries and packages that are used in the examples of the notebooks we developed for the MOOC. So, but this gives you a better understanding. Okay, what is the difference to TensorFlow, which is more like a machine learning framework, and then Keras is a specific API that is built for deep learning applications, for example. Then PyTorch is just a machine learning framework, which is just like a more general again compared to Keras. And then scikit-learn again is also a machine learning framework. And with this, I would now basically just start the break for 10 minutes. We are now a bit over 11:20, but nevertheless, I would suggest to maybe have like 6 minutes break, and we could come back at 11:30 Central European Summertime. And then I will specifically introduce you to practical application examples that are part of the MOOC that was developed and run last year. Thank you.
Excellent. Thank you so much. And we're going to take a short break, as you've mentioned. Yes.
See you at 11:30 CEST.
So we got 5 minutes, correct?
6.
6.
Maybe 5.5. I'm not too sure. Anyway, time to get a glass of water, a juice, a soft drink, or a coffee. See you in a short while.
Okay, welcome back. I hope the break was enough.
You're on mute.
Am I muted?
Oh, sorry. No.
That's okay.
My mistake.
Okay, good. Okay, welcome back. I hope 5 minutes were enough, but at least hope you could fetch something to drink or get up shortly. And now we go to the practical part where I introduce you to some of the practical examples we developed in the MOOC. I just saw there was one question also on Slido specifically to which Python libraries are recommended to use for machine learning and artificial intelligence. And I would just respond to this question because this is just in line what we just discussed before. And I just saw here the question is which Python library is better to use, or do we have to use all? And I understand the question that it can be quite confusing because there are so many different libraries out there. And what we also say here in the notebook is basically, so each framework and library has specific strengths and weaknesses, and which one to use strongly depends on your purpose and also goal of your machine learning application. And so, and there's basically some people, they're just big fans of TensorFlow, others, they're just more familiar with using PyTorch. So I would always choose it based on, first of all, to once you know what algorithm you would like to use, to look which library or framework offers a specific functionalities for this algorithm. And it's also always helpful to also see how maybe others already use this specific library for similar problems, because then there is a bigger community behind, and you also might, if you run into problems or questions how to set up the specific algorithm or functionalities, then there's the likelihood just higher to also find support on Stack Overflow, on the documentation of the specific framework or library. So this is definitely not that you have to use all of them for one problem. And this is also what you will see, that basically each application just uses one specific framework or library because the developer just made this choice, because sometimes it's also about simplicity, right? So you don't have to go for the most complex version if there is maybe a very simple implementation in scikit-learn, for example. So it's really also at the beginning, once you start and look into which framework or library to use, to really also evaluate what is the best choice based on your purpose and also goal of your application. I hope this responded or this answered your question. Okay. So basically, we are back in our Jupyter Hub environment, and I just close this example, and I go back to my working directory in the public folder, just as a reminder, and then in the machine learning one, we have our overview of the different application domains for each week of the MOOC, and I would propose to start in the week 3 in land applications, and specifically in the last example on land cover classification with Sentinel 2 data. And if you go there, you will see 2 notebooks, one that introduces you to supervised classification and the other one that introduces to unsupervised classification algorithms. And I opened here the notebook on supervised classifications. And this is what I will walk you through now, because this is basically a very nice overview notebook that introduces you to different and popular algorithms that are used for supervised classifications, and also a very nice overview on the different steps of developing a workflow with creating training data sets and validation data, etc. And so, this workflow and example was developed by Artur Nowakovsky from the Warsaw University of Technology, and it introduces you to an example of a supervised land cover classification with one Sentinel-2 scene. And so the aim is to classify a Sentinel-2 image into 4 different land cover classes, into water surface, so to differentiate each pixel of the Sentinel-2 file in one of these 4 land cover classes, so either water surfaces, artificial surfaces, low vegetation, or tree cover. And supervised classification means that an algorithm is trained based on labeled training data and then validated with these labeled validation data. So this means basically we have to prepare a training or labeled data in beforehand on which our algorithm can learn from or train the algorithm, and then afterwards, once the model has been trained we can then apply it to another Sentinel-2 scene and see how correct the classification has been done. And so this is also important to understand here that like both the training validation data and validation data, they have been prepared manually. And this is also the case in many of these examples, that we have to prepare first labeled data, which we can train the algorithm on. And this notebook specifically shows you how you can basically train, classify, or predict, and then evaluate based on 3 different supervised algorithms: decision tree, random forest, and support vector machine. And then, so the data that is used is that a Sentinel-2 image subset was pre-processed. And in order, or the data that is used here, some pre-processing steps have been executed. And here we also listed these pre-processing steps. So first of all, it was subsetted to a dimension of 200 × 600 pixels. And all the 13 bands of a Sentinel-2 image have been resampled to a 10-meter resolution, so that all 13 bands are on the same resolution. And then these 13 bands have been saved as individual TIFF files. And then additionally, a set of training and validation data points have been manually identified. So if you go to training data, so if you go here to the Sentinel-2 data, you see here the 13 different TIFF files that have been prepared, what we described here. And if we then go to training data, you see for each of the classes a text file, and if we open one text file, then you see basically 100 points with latitude and longitude locations of or with X and Y location points for each of the land cover classes. So for artificial surfaces, low vegetation, tree cover, and water. And then we go back, and if you open validation data, you see here one text file, which again contains 100 labeled training point locations together with the land cover class. So basically we see here, this is used then for validation. We have here again X and Y information, and then a land cover class from 1 to 4. And so this has been manually prepared at the beginning. And then the first step is all, and this example uses, for example, scikit-learn, and because scikit-learn offers all the algorithms that this workflow uses, so decision trees, then the support vector machine, etc. And so so this is example where you can learn how to use scikit-learn, the scikit-learn library. So the first step is to load and display a Sentinel-2 image. And if you remember, so there is just an overview of the different 13 bands in visible, near infrared, and shortwave infrared spectrum. And they have different spatial resolutions, just as a reminder that the data, they all have been brought to the same spatial resolution of 10 meters. And so if we open this pre-processed Sentinel-2 image, then we open basically all the different TIFF files that are in the folder s2_data. And if we then build a composite, a true color composite out of the bands 2, 3, and 4, then we see here our subset of the Sentinel-2 image. And the next, and this just gives an overview on the image which we want to train the algorithms on. And then just to also get an overview on the training points and validation points, we load here the training point locations for all the different land cover classes for water, artificial surfaces, low vegetation, and tree cover. Important here is that basically what you already see, that so you see here now hopefully different colored pixels in blue, green, red, and yellow. And the yellow ones are here for the low vegetation. The blue ones are for water. The red ones are for artificial surfaces. And then the green ones are for tree cover. Important for training points here, this is also a nice overview, is that basically that you try to find on each of the part of the image so that like you really nicely distribute the training points on different aspects of the land cover class. And then basically the next step is then to transform the training labels into a format that the machine learning algorithms for supervised classifications will understand. And the algorithm in principle requires an input and an output variable. So the input is the X variable and the output is the Y variable. So the land cover class, which we want to predict. And so the output will be one of the 4 land cover classes, and the input variable, we take for each of the training points, the information of the 13 Sentinel-2 bands. So for each of the latitude and longitude points, which we indicated here as a training point, we use the information we receive from the 13 Sentinel-2 bands. And then the resulting array has a shape of 400 times 13, which contains for each of the training points of the four for the four land cover classes, the data information of the 13 Sentinel-2 image bands. And this is also here a figure that indicates the example and the transformation process. And so then we basically in Python, we guide you through how we can make this transformation step, and we repeat the same step for the four different classes. So for water, artificial surface, low vegetation, and tree cover. And then basically we are in a position to define and also to train the three different supervised training classifiers, where we want to train decision trees, random forest, and support vector machine. And so, as I said already, like the frameworks and libraries that are offered by Python, they already have a lot of algorithms defined that, and so this can be also quite easy to actually implement. So here the first step is, for example, to train a decision tree classifier, and you can use the tree module from the scikit-learn package. And there is, for a lot of algorithms, you can specify a lot of hyperparameters or keyword arguments. But here the simple example just uses the maximum depth, which defines the maximum depth of the decision tree, which we set here for 10. But specifically, if you are new to machine learning, then this is also one of the aspects to play around with these hyperparameters. So these hyperparameters are basically where you can fine-tune your algorithms. And so the example here just shows you one hyperparameter, and you can play around about how does the result changes if you develop a decision tree with a maximum depth of 10 compared to if you develop a decision tree with a maximum depth of 5, for example. And we also always recommend you to also have a look to the documentation for additional hyperparameters, which you can, and as I said, this allows you to really fine tune also your classification and your algorithm in general. And so once you defined the decision tree classifier, you can then train, or you often will hear fit the classifier onto your input and output data. And this is what we basically do here. So we apply the function fit. We give our input data, the x, and then we basically give our output data as y here. And then you can use the function plot tree to visualize the trained decision tree. And there's again, we give some examples how you can specify or how you can specify specific keyword arguments. But this is basically here then the decision tree that has been developed with a maximum depth of 10 different layers. So this is a decision tree, and you see basically from the scikit package, it's super easy to apply the algorithm because it is already also available as a predefined algorithm. And the same is also for the random forest classifier. So the next example here shows you how you can define and train a random forest classifier. This is a very common algorithm used for supervised classification. So instead of fitting only one decision tree, subsamples of data are fit to a number of different decision tree classifiers. And then the average of the different decision tree classifiers are used. And you can set up here also simply, again, a random forest classifier with the ensemble module. And as an example here, we define the following hyperparameters. So number of estimator, which is the number of trees we want to use for each prediction, then again the maximum depth, so the maximum depth of our tree, and the random state, which controls a specific randomness of the bootstrapping of the sample. So this means that basically we don't just initiate the same decision tree with the same data for our ensemble prediction. And then again, we can, so we here specify or define our random forest classifier, and then we fit it onto our input and output data again. And then here again, we can also plot a tree to visualize the first n trees from the trained random forest. And so this is one tree that has been developed, and you can indicate here already some differences on how the tree was developed. And then basically the ensemble of the different number of training or decision trees that have been defined and developed is used for the final output. And then the support vector machine classifier, it's again here we can use the SVM classifier, which builds a so this is a bit of a different approach, but it builds a hyperplane feature space to separate different classes. And from the scikit-learn SVM module, you can use the SVC class. And this offers you functionalities to develop and define a support vector vector classifier. And then again, you can use the function fit to fit the support vector machine onto your data. And this is done here. And then the next step, so after you trained your algorithm with the 3 different classifiers, you can use the trained models to predict or to classify the land cover of a Sentinel-2 image, which we inspected at the beginning of the workflow. And but for this, we have to again transform the Sentinel-2 band collection into a format that a classification function can read. And so in principle, the transformation we have to do is to flatten each of the images. So each of the Sentinel-2 bands, we have to flatten. And the result is a multi-dimensional NumPy array with 13 rows, and each row containing a 1-dimensional vector with 120,000 entries. And 120,000 is basically the number of pixels. So 600 times 200. But we have to, instead of having it in a 2-dimensional space, we need to have it basically for each of the bands in a 1-dimensional vector. And this is done here. So we have basically a NumPy array with 13 rows and then 120,000 entries. And then we can apply the function predict to use for each of the classifier to predict and classify the Sentinel-2 image into the 4 land cover classes. And the resulting array has then a shape of 120,000 rows containing the predicted land cover class for each pixel of the flattened Sentinel-2 image. So for each of the pixel, we then have a number of 1 to 4. And so then as a next step, we can visualize the classified image, but we need to again reshape the array into a 2-dimensional dimension, which basically resembles the original Sentinel-2 image. And for this, we can use the function reshape, and this is what we do here. And then we can plot the original true color composite, what we saw at the beginning, together with the predicted land cover classification, followed by a legend helping to interpret the land cover classes. And this is how basically the first decision tree classified or predicted each pixel or assigned a specific land cover class, and based on the training points we provided. And so here the color code here is that like dark blue is water, then blue is artificial surfaces, which what we see here basically is that we have here an industrial area, which is also indicated in our classified image. Then green is low vegetation. So here we have like a long stretch of low vegetation, which is also indicated here in our classified image. And yellow is a tree cover, which basically, if what we see here at the end of this long stretch, it seems that there are trees, which also has been picked up by the algorithm. And then the notebook basically repeats the same prediction step also with the other two classifiers. So the next example would be the random forest model and predicting the land cover with the help of the trained random forest model. We again have the same reshaping step to reshape the predictions to a 200 times 600 two-dimensional image again, and then we can plot again also the prediction that has been done with the random forest classifier. And here again, so there's you could also basically then compare the two different predictions first visually, but then at the end we will also show you how you can actually also validate the quality and the quality of the predictions of the classifier. And then the last step is here to also predict with the support vector machine model. Again, here the same steps, and again here also the outcome of the predictions with the support vector machine algorithm. And then the last step is because now we know somehow, okay, it was predicted, but we also don't know how what is the accuracy of the prediction in general. So because it's quite hard to visually recognize if everything has been accurate, and so this is a natural next step for many of the supervised classifications to evaluate the performance of the three classifiers, and this helps you to better assess the accuracy of the land cover predictions. And the evaluation is, and for this reason, we need the validation data points, which I showed you at the beginning, that has been defined basically, where we have for each like 100 validation points, and for each of these validation points, we also have for sure the correct land cover class. And these validation points were manually selected, and I also showed you already. So the first column has the horizontal pixel coordinate, then the second column has the vertical pixel coordinate of the validation point, and the third column is the land cover class index, so from 0 to 3. So 0 for water, 1 for artificial surfaces, 2 for low vegetation, and 3 for tree cover. And so here we load the validation points, and then again here we just showcase how the validation points are distributed over the Sentinel-2 image. And here again, this is very important to not only focus the validation point in one specific area, but trying to really spread them across the entire image. And then with the help of the validation points, we can evaluate the accuracy of the three land cover classifications. And two metrics that help us to do this is the overall accuracy and the confusion matrix. And with both metrics, you can compare for each of the validation point locations, the true land cover class with the predicted land cover class for the same pixel. And so here in a first step, for each of the validation points, we need to retrieve the predicted land cover class from each of the three classifiers, what we do here. And in a first step, we calculate the accuracy score for each of the three classifiers. And for this, we can also use from the scikit package, again, a function that helps us to calculate the accuracy score, which is part of the metrics module. And we see here that for each of the overall accuracy, so like the accuracy of all the pixels classified with the 3 different algorithms, is quite similar. So for the decision tree is 84% of the pixels from the Sentinel-2 image have been correctly classified. And for the random forest and support vector machine, it's even 85%, but almost like all quite close. And then another evaluation score is the confusion matrix. And this calculates the confusion matrix between true and predicted land cover classes with the function. And here you can also use a function that is already available from the scikit-learn package. This is called confusion matrix. And with and then you can also visualize this confusion matrix, because this often is quite a nice visual way to also indicate which classes have been correctly labeled. And this helps you to better understand which land use classes are classified well by a trained classifier and which ones are falsely classified. And here we basically then create a confusion matrix for all the 3 different classifiers. And this, compared to the overall accuracy, this gives you a much more or a better detailed overview on which classification or which land cover classes are maybe better predicted compared to others. So this was a first example on supervised classifications for the land applications. I would now go on to another example for example, because this is like just a very different example and more on a scientific application on retrieving methane from Sentinel 5P data. And so this is more like of a, so this is, if you go to the overview, this is part of the atmosphere week, so of week 5. And there are 2 examples to predict or to estimate ozone concentration. And then the second example is to retrieve methane with the help of Sentinel 5P. And so I just chose this example because this is just a different approach and a different application example for how you can also develop or why you would need machine learning as well for so there's a different example compared to land cover classification, which is a very popular example. And here, this example is basically showcase you that, so in general, to understand physical processes that occur at the Earth's surface, you often use physically based radiative transfer models. But these models, they can be quite computational intensive to actually run, and they can also get quite complex, and so they can take a long time to run and often makes it quite unfeasible to use in operational context. And so a very common approach also is to replace these advanced radiative transfer models with emulators. And an emulator is a statistical model that can approximate the advanced radiative transfer model. This can be quite useful because, first of all, it dramatically improves and minimizes the computational runtime and also speeds up retrievals of the specific parameters. And this example showcases how to retrieve greenhouse concentrations and estimations based from Sentinel 5P data. And so and for creating such emulators, machine learning can be used to develop a statistical model that approximates this radiative transfer model. And this notebook exactly takes you through an example of generating an emulator of an atmospheric radiative transfer model called LINTGAN. that is used operationally to retrieve schemes for methane. And so this workflow makes use of the MLP regressor class from the scikit-learn neural network module. And this is a supervised neural network algorithm. The data that is used is also described here in detail. So as said, this it uses the Remo tech algorithm that simulates a realistic approximation of the Sentinel 5P Tropomy bands. And it is currently operationally used to retrieve methane from Sentinel 5P and Tropomy. And the core of this algorithm is the Lintran radiative transfer model. And this simulates synthetic spectra based on a set of input atmospheric spectroscopic surface and instrument parameters. And we also linked you some of the information to also get a better understanding of this quite scientific or complex also problem on how you can also use machine learning to approximate radiative transfer models. And so in order to emulate the Lintran radiative transfer model, 50,000 simulations have been performed. On these simulations, they are available as training data for this specific example. And you see here also which the key atmospheric parameters that are available for the machine learning algorithm to train and estimate or approximate also the radiative transfer model. And so this is basically the training data set that is available. And here again, we always start with importing libraries and also helper functions that are used for the example. And then, so if we go to the specific folder here, and you see here that the methane data set is available as an NPZ file, which is also a format that is commonly used for machine learning applications, which is in principle a zipped archive of different variables. And the file contains here the following parameters. So a state vector, which is an atmospheric parameters that is used for the input for the radiative transfer model, then wavelength of the output radiance from the Tropomy shortwave infrared band, then the spectra, which is a radiant spectra output from the radiative transfer model, and then the number of data set, which is the size of the data set, so the number of simulations, and the number of atmospheric parameters used in the study. And so here basically we load the data set and the different parameters, and we see here then also the dimensions of the different parameters. So that we see here, for example, we have up to 125 different atmospheric parameters that were used in the study and can be also now used for a training data set. And so so just is also like a common approach is also to first visualize the data which we work on and which can be also used as a training data set just to get a better grip on what we're actually working with. And here we visualize the example of the simulated Tropomy radiant spectra, so top of the atmosphere radiance in the shortwave infrared band. And this is also the band which is used to retrieve methane from Sentinel 5P data. And so this is basically here the radiant spectra in the shortwave infrared band. And so the next step is then to split the sample data into training and testing subsets. And this is also a very common function which you will use in many of the machine learning applications, which you can use from the scikit-learn library to use the function train_test_split, because this function helps you to split your training data set into input parameters for the machine learning model, into output parameters for the machine learning model, and then to have like test and for testing and training data sets. And so this is what we do here. We want to train our neural network based on the state vector information, which is our input parameter. And as a reminder, the state vector information is in our training data set, and the spectra information is the output parameter. So this is what we want to predict. And and you can then also specify in this function the relative percentage. So so how much percent of the training data set should be used as a sample data for validation. And this is the example. So for like 10% of the sample data will be used here for validation, but you can, and 90% will be used for training. So this is also a parameter which you can basically play around with, which is often also good to get a feeling of what is a good percentage and differentiation between training and test data. And so if you then inspect the array sizes of the training input and the validation input, we can see that out of these 50,000 simulations, 90%, 45,000 are used for training, and 5,000 samples are used for validation. So samples train is training, and samples validate is for validation. And then a next step is to, these are also often some pre-processing steps required for quite a few machine learning algorithms to standardize or scale the training data. And this is a common operation in machine learning, especially if you have diverse input parameters with different data ranges. And because this is it's needed because it might, or it often behaves badly if the individual features do not look like a standard normally distributed data, for example. And there are different functions available to standardize or to scale data, or to bring them also into one data range. So the example here shows you how you can apply the standard scaler, which is also a class from the scikit-learn's pre-processing module, to scale the data based on the average and the standard deviation of the data. And first, you have to initiate or define a standard scalar, and then you fit the scalar to the data with the function fit. And then you can also transform the scale data with the function transform. And this is what is done here. And then this can be also repeated for the training data and the validation data. And then this example also shows you an additional pre-processing step because the amount of the input data is quite large. And often if this is like if you have a lot of input data, you can also have another pre-processing step that reduces the redundancy and also collinearity of the input data, and you can basically apply or classify already the large amount of input data into principal components. So you apply a principal component analysis on your input data. And this is done here in this step. So we apply this onto the input training data, and you can then also set the number of principal components you want to classify or cluster your data into it, which is set here to 20. And so the dimension of the scaled training output data is then reduced from 45,000 times 800 834 to 45,000 times 20. So instead of 834 feature, we now reduced our input data as into 20 principal components. And so then in the next step, you can then set up and train the neural network. This workflow shows you a scikit-learn neural network function or algorithm from the neural network module called MLP Regressor. And this algorithm is called multi-layer Perceptron Regressor. And here you see that the example uses quite a range of hyperparameters and also keyword arguments in order to define the algorithm. And again, so this is basically a fine-tuning of your algorithm, and I can just invite you to also play around a bit with these hyperparameters in order to also see how your output changes if you do a different setting of these specific hyperparameters. And then basically you get here, again, you can get an overview of all these hyperparameters set and defined. And the training process of the model is also often called fit, and also the function is often called fit. And so we apply here, so this is where we train the model, we use the function fit, we give our training input data and then our output training data to train the model. And then as a last step, you also can save the trained model. And this is often helpful if you want to use the trained model also later on for different applications, then you can also save your trained model. And in the next step, instead of going through all the processing steps again, you can basically save your trained model. And then again, the next step is to predict and evaluate the performance of your trained neural network. So the trained model is also being made available to you here. So in case the training might take a long time, which can happen. So don't panic if you execute a cell and nothing happens. So this just means that basically the algorithm is just processing, and it often can take a couple of minutes for the algorithm to actually train the data and to be trained. And so for this reason, we also provided you already pre-trained models, which you can then open. And then again, we can apply the function predict to predict the spectra with the loaded pre-trained model and also the validation input data set. And then this is also, of course, like because we applied these pre-processing steps. So the next step is then to reverse these pre-processing steps. So to reverse the scaling and also the principal component analysis. And this is what we do here. So we first inverse the principal component analysis, and then we inverse the scaling. And as a last step, we can then evaluate the model performance. Here we use two other metrics that are quite common to evaluate machine learning outputs is the root mean squared error and also the normalized root mean square error. And we see here that the overall accuracy of the training is around 62%. And we have like here quite a low root mean squared error and also normalized root mean squared error, which is quite good. And then in the end, as a last step, you can also visualize the predicted spectra and compare it visually with the model output. And to also see that you basically see that it follows quite, so the output from the neural network follows quite good also the spectra developed by the Lintran radiative transfer model. And yeah, so basically with this, I would now stop the practical demonstration. I I gave you an overview of two quite different examples. Again, I really invite you to go to Wekeo and also have a look through all the machine learning examples that are available there. And as Neil also said, to provide feedback, because it's always good to better understand how helpful also this training material is for you. And I hope, yeah, you enjoyed it. It was helpful to get a nice overview, and I am happy to answer any question. Thank you.
Thank you so much, Julia, for your presentation. In fact, while you were presenting, some compliments were being posted in the Q&A or in the chat about how clear your presentation was and how well designed was the material available on Wikio, and how easy it was to follow the various steps that you described after registering. So thank you so much. For the time being, I see, well, first there's a suggestion from Omar Valencia in the Q&A that I invite you and Neil to read, which basically says it would be helpful if you added information about what the code is actually doing so that people can understand the mechanisms. I'll let you possibly comment on that. There's a question to which I'll give a general answer, and I'll let you also come into more details. The question is still from Omar Valencia. Do we have access to the satellite data since which the date on, from which date on? Is it all the historical records of the Sentinels or only the last weeks? There, through Wekeo, you have access to the entire archive, but there is a difference between, I would say, rather recent data, and I don't have the exact numbers in mind, but recent data in particular for Sentinel-1, which is extremely memory intensive. You need a lot of storage, basically, because the tiles, the synthetic aperture radar tiles, are so big. So recent data is available instantaneously, and you can visualize it in the platform, and you can download it in no time. Older archive for some of the satellite data sets is available, but it's a query that you make, and the system makes it available for you, retrieves it basically from an offline archive in a very reasonable amount of time. So that's my general answer. Anything Neil or Julia want to add to this?
I would just say that we do have, there's a tutorial that one of our colleagues, Haley Evers-King, did that we put on YouTube, and it explains how to choose a spatial area of interest and also look at the time frame that you're interested in. So I think that would be a good place to start. I'll see if I can find it and put it into the chat for you.
Okay, but in principle, again, it's. I see also that our colleague Amin and Amrani is available. Amin, do you have the numbers? Well, the dates for what's the time range of the immediately available archive, and the because otherwise the archive, since the data is operational, the satellites are operational. So Sentinel-1, if my memory serves me correctly, we're talking mid-2005 for the beginning of the.
Actually, I think the data is available for 6 months on Sentinel-2 and Sentinel-3 for sure, and it actually depends on the data set. So it's not the same for all the data sets. I think that's all.
Okay, so again, I confirm that you have access, immediate access and visualization of the data, the recent data, let's say, and 6 months is kind of the average of the average age of the archive, while the rest is available just through a query that makes it. I don't know how long it takes because I'm not an expert, but it's like it's this when the specification is it has to be compatible with operational use of Sentinel data. So it's not a matter of weeks, it's a matter of hours or maybe one day, something like that. There's a second question from what Zoom calls a anonymous participant. Is it possible to use the Wekeo platform and other remote sensing products along with the Copernicus data? I need to use the ready-made notebooks and apply random forest algorithm for my study. Thanks. So again, I'll stay at the level of the theory and let the expert answer the question. You can basically upload any kind of data into your environment, your Jupyter notebook, etc. In fact, we have been looking into the possibility of directly allowing access from Wekeo to very high resolution commercial imagery. That's something we're looking into. So in principle, the answer is yes, definitely. It's not you could import either commercial imagery or Landsat if you need a time series that go back rather far in time. But any compliments from the experts?
I can say a few words maybe. So if you want to see all the data that is available, you have to check the catalog. If the data is there, it means that it can be downloaded through Wekeo. If it's not the case, as Stefan was saying, you can download basically anything on your virtual machine via another way, and you can get your data and then do whatever can be done with this data, even if it's not from Copernicus. It can be stored and used. That's all.
Okay, thank you. I mean, there's a question from Sebastian Konza. I would be interested in the detailed process of creating and loading the training and validation data set.
Yeah, I can respond to that. So basically, what you showcase, like that, there's no one approach that fits all, and so all the applications, they showcase pre-prepared data, and this is like specifically done for this specific application. And sometimes it is really like a long, tedious process of what I showed the example with the land cover classification. This was just like, okay, this was 100 points, so this could be done. Like, okay, maybe in some hours, but sometimes it's really getting labeled data. It is a very long time process, which can also take 2 months. So as a suggestion, we could think of how to explain it more in detail. So like to have the detailed explanation steps, how everything was done. To really reconstruct it with the example what I presented today. This could be probably done also by individuals and going through the course. With other examples, you will see they basically provide you already entire database of training labeled data sets. So this is also like a part of machine learning and research, that like a lot of research groups, they work months, sometimes years on publishing labeled training data set for ship classification or land cover classification. So we also showcase you some labeled training data set which you can already use, like the example under the land week for the Eurosat data set. The Eurosat is specifically such a labeled training data set. So yeah, thanks for the proposal. We will have a think about how we can maybe make this a bit more obvious, but it is not straightforward to also guide you through this process, because it is, what I said, actually the most time-consuming part to have good labeled training data.
Thank you, Julia. There's a question from Musan Gosha. Would like to know if we can demonstrate how to prepare the data using Copernicus satellite data, and he's specifically referring to the training set and the test set through the Wekeo platform. I think you partially answered the question, Julia, but any additional comments you would like to make on that?
I think it's like really also the same comment here. yeah, if possible, but it will be what I said. We can have a look on if possible for some of the workflows. We can really make it a bit more detailed. But for some, we also already use these pre-prepared labeled training data set for some applications. And there we basically make you these labeled data set already available, which also are part of a public repository. So it's a good comment, and definitely also needed if already to also mention this, and we could definitely think about how to make this a bit clearer and maybe also showcasing different examples how data can be prepared for training and validation.
Thank you very much, Julia. I think we have exhausted the time allocated to Q&A, and anyway, there are no new questions. Some comments. Great tool and presentation today, Omar Valencia. I hope that it is integrated into more applications and some tutorials MOOCs which are prepared in the future. Well, definitely the subject is of high importance and interest, again, because of the mere amount of data that is becoming available and the long historical data sets, and because of the ability of AI to, for instance, bring super resolution. I mean, there are applications today who are allowing to have something close to 5 meters on Sentinel-2, at least on the RGB bands. Some scientists even claim better results. So that's basically extracting more data, being able to extract more features from the available data. So that's definitely a trend of the future. And Wekeo in particular, and I mean, the Copernicus ecosystem in general will certainly work in also because of the evolution of the technology and the new algorithms coming up and the new discoveries being made. We will certainly in the future continue to provide resources on use of artificial intelligence within Wekeo, and I'm pretty sure that the team will, in the coming years, make more training webinars on the issue. So to conclude this webinar, I'll quickly run through the next events. In fact, there is only one event left on the 30th of June, at least from the ongoing series, and this one will be on the new products that are available in Wekeo. The catalog is constantly evolving, so we'll showcase and even possibly show you some Jupyter notebooks that are being finalized. What are the new products that are there that are recently ingested? We'll possibly also discuss for some major data sets like Sentinel-6, the short-term and medium-term plans. And there's a few new products also for Mercator, for the Marine Environment Monitoring Service. There's also some UETSAT new products. So all of those will be showcased and presented on the 30th of June. So we hope to see many of you in that webinar. Again, Neil put a comment in the chat, but we encourage those of you who are into Jupyter notebooks to look at the competition that UMETSAT and Wekeo has launched. You have until the end of July to submit your Jupyter notebooks. There's a 5,000 euros prize pool, significant, I would say, for such a competition. We already have quite a lot of really interesting entries, but the competition is still open, and we hope to see many of you participating. So once again, thank you so much to our presenters, Julia, Neil. Again, there were lots of compliments in the chats and in the Q&A, and some of them from senior members of the community. So I'm grateful to them for telling us that they like what was presented. It was also very thrilling to see so many of you, and not only Europeans, like from the names at least, I saw some participants that are at least originally from Africa or from Asia or possibly from South America. So really interesting, and we're really happy that you participated, and we hope that you are going away from this webinar with lots of ideas and insights into how to use Wekeo, Copernicus, artificial intelligence to crack some of sometimes detailed or sometimes grand challenges of our time. And of course, biodiversity, climate change, etc., are on top of that list. Thank you again for being with us, and see many of you hopefully on the 30th of March. Joanna, can you keep panelists in for just 1 sec? Is that possible?
Yes, hi. So again, it's like in the previous.
Oh yeah, true. It's not possible. Okay, I'll
Right,
just send
so
you. I'll send you a Teams invite,
Yeah.
so we can just have 3
Thank
minutes.
you all. Have a
Thank
good
you,
day.
Joanna. Thank you, Neil and Julia. Look for the Outlook invitation, which I'm sending right
Yeah.
now.
Okay.
Okay, thank you. Bye.
Thank you.
All right.